Identify the correct statement from the following with respect to RLC series circuit under resonance condition. So we know pretty well here, under resonance, what happened, particularly series resonance, under resonance in series RL circuit, what will happen? Inductive reactance will become exactly equal to capacitive reactance, so that the impedance Z is equal to R plus J X into XL minus XC. Since XL is equal to XC, this net reactance becomes 0, then impedance become purely resistive. Impedance become purely resistive. So impedance is becoming purely resistive means here both applied voltage and current will become in same phase. In that case, theta becomes equal to 0 degrees phase. There will be no angle difference between voltage and current. So then power factor cos theta will be equal to what here? Unit 1. So under resonance we are going to get what a unity power factor, no doubt in that. And if we consider the current flowing to through the circuit under resonance, I naught equal to V by Z means here V by Z. But here since reactance part is becoming 0 here, Z is going to become minimum. Z is going to become, so that current will become what? Maximum. So under resonance condition in series RL circuit, maximum current will flow, right? And see here, just go to the statement here. Identify the correct statement from the following with respect to RLC series circuit under resonance condition. Power factor of the circuit is unity. Of course, here power factor circuit is, and this is a correct statement only. All the voltage, all the applied voltage appears across L and C. This is a wrong statement. Why? Because the net voltage is given by V is equal to VR plus J into VL minus VC. Since XL is equal to AC, equal voltage will be applied to the inductor as well as the capacitor, so that this particular term will get cancelled. So total voltage will be applied across resistance only. So this statement is wrong. Current in the circuit becomes maximum. Of course here, since the impedance is becoming purely resistive, the impedance is going to be reduced here. So under series resonance, the impedance is minimum, so that current is maximum. This also correct statement. At half power frequencies, half power frequency means here, say if you observe the variation of the current as well as the current versus frequency, you may get like this here. So current will get with a maximum value at a resonant frequency here. If you see on either side here, so current falls to a value of Im by root 2. So the corresponding frequencies are known as what? Half power frequencies, F1 and F2, right? F1 F2, and at these frequencies usually power factor is what here? 45 power factor angle is 45 degrees. This is also a right statement. So A, C, D statements are right statements. So except statement B here. So A, C, D. Where is it? D, A, C, D means here. So given mentioned in option 3. So option 3 is the right answer. Next question here. Match the following with respect to measurement of power in a three-phase circuit using see here. So clearly in measurement of three-phase power by using 2 watt meter method. What about the power factor angle here? What about the power factor means here? Power factor is equal to cos theta, where cos theta is, again theta is, it is a tan inverse of root 3 into W1 minus W2 divided by W1 plus W2. This is where W1 is what your watt meter, first watt, it is reading of first watt meter, and W2 is reading of second watt meter, right? And we need to match here. So we need to find the power factor current. First option L here. Option L means W1 is equal to 0 and W2 is equal to WT. So here option L here, W1 is equal to 0 and W2 is equal to WT. Then what about power factor angle here? Theta is equal to tan inverse of root 3 into root 3. In place of W1 I am substituting 0 minus, in place of W2 I am substituting WT by 0 plus WT. What happened here? Minus WT by plus WT means here what happened here? It is minus 1 here. Minus root 3. So we got here tan inverse of minus root 3 means here tan inverse of minus root 3 means minus 60 degrees. So then power factor cos theta is equal to what here? Cos of minus 60 means here cos of minus 60, cos 60 only, cos 60 equal to 1 by 2 means 0.5. So here we are matching, I am matching here when for wattmeter 1 reading is 0 and wattmeter 2 reading is WT. So the power factor, corresponding power factor is what here? Yes. Then L is mapped with what? L is matched with what? Yes. Then next case W1 is equal to minus W2. Second case here M case W1 is equal to minus W2. In that case theta is equal to tan inverse of root 3 into W1 value minus W2 value as it is by W1 plus W2 minus W2 plus W2. What is going to happen here? In the denominator we are getting 0. Anything by 0 means what? Infinite. So tan inverse of infinite means it is 90 degrees. Then power factor is equal to cos theta is equal to what? Cos 90 is equal to 0. For this case we got what? Power factor value is 0. When W1 is equal to minus W2, power factor is what? 0. So it is mapped with what? Q. So MQ. Let's say MQ. The last thing is what here? W1 is equal to 2W2. Then here W1 is equal to 2W2 means here what about theta here? Tan inverse of root 3 into W1 minus W2 means 2W2 minus W2 by 2W2 plus W2. So what will happen here? It is W2 by 3W2 is equal to tan inverse of root 3 into W2 by 3W2 means this will be tan inverse of root 3 by 3 means here tan inverse of 1 by root 3. 1 by root 3 means here 30 degrees. It is 30 degrees. Then what about power factor here? Power factor is equal to cos theta is equal to cos 30 degrees is equal to what? Root 3 by 2. It is numerically equal to 0.866. So here, so for this case the power factor is about 0.86. So N is mapped with the P here. So LS MQ NP. So where it is here? It is clearly mentioned in option 2. So option 2 is the right answer. Next question. In the circuit shown below, the voltmeter reads 100 volts. The reading of the ammeter. See, the voltmeter is reading 100 volts means it means that here voltage clearly known that voltage across this 5 ohms resistor is what here? 5 ohm resistor is clearly how much here? Voltage across is 100 volts. Then what about the current flowing? This assume that the current is your I1 here. I1. So I1 is equal to voltage across this resistor is here 100 by resistance is what here? 100 by resistance 5. So means it's 20 amperes. So here what happened here? This is this 20 amperes. This is 5 minus J5 and this 5 plus J5. Both branches are having same magnitude. That's why same current will flow here. So I2 is also equal to what here? 20 amperes. And what about the net current means here? Since it is an AC circuit, ammeter usually reads what here? RMS values of current. So I is equal to here square root of I1 square plus I2 square. If it is DC circuit, you can add up directly. I is equal to I1 plus I2. If it is a DC circuit, but it is AC circuit, that's why I is equal to root of I1 square plus I2 square means here root of 20 square plus 20 square means it is root of 800 means here it is 10 root 8. But root 8 is what here? Simply root 8. 10 root 8 means here 10 into 2 root 2 this one. So it is 20 root 2. 20 root 2. What amperes? Where it is here? It is given option A, option 1. Right. Again here he has mentioned. So it is 20 root 2. Right. 20 root 2 amperes. So option 1 is the right answer. For which of the following combination of the circuit element the average power drawn from the AC supply will be 0? Generally, for pure inductors here, the power dissipated by a pure inductor is always 0. The power dissipated by a pure capacitor is always 0. Similarly here the power drawn by a pure inductor over a complete cycle is 0. So here pure inductance capacitance is done, but for parallel LC combination also the power drawn from AC supply will be 0. LC parallel combination also the average power drawn from the AC supply is 0.
130. If the core of the transformer where the square core is used and circle represent the tabular form of the carrying coils, if the maximum cross sectional area of the core is 0.5 d square, then the side A. So now we required the side A. So what is the value of the side A here? A is the side of the cross sectional area of the core, and this one is the winding. So this one is winding, and this square is nothing but the core. So winding place around the core as shown in this figure. So this type of the core is known as cruciform core or stepped core of the transformers. So this one, how do we find out? Suppose if it is a here and this size also A. Now we require the diameter. Suppose this is also diameter. So this one is the diameter of the circle. So how do we get the D value here? The D is equal to under root of the A square plus A square. So now where D is equal to diameter of the circle. So now this one is A square plus A square, that is a root 2, the A 2 times of the root 2 times of the A. Now A is equal to root 2 times of the A, and next one we know that given also the cross sectional area, cross sectional area of the core, the area of the transformer core. So that is equal to AZ is given. So this AZ value is equal to 0.5 D square. Now how do we find out this square, the square area here? So now we know size. Suppose A square the multiplied by this one is the A square, the 0.5 D square. Now we required A value, where A value is equal to, so this one under root of 0.5 times of the D square. So therefore A is equal to, so this one is the 0.707 times of the D, the nearly equal to 0.7, this one is 0.71 times of the D. So option the here. So this area is required. Here no need to find out diameter. Suppose if it is asked about the square, we can find out the area also, area of the, so this circle. But we required only size of the A. So this area is given directly 0.5 D square times. Now this area we can write area of the square is equal to A into A square. Now what is the relation between these two? A square is equal to 0.5 D square and A is equal to under root of 5, 0.5. So that is equal to 0.71 times of the D. So option 3 is the correct for this question. Got it? And next one, let us solve the question number 131. While conducting open circuit test on a single phase transformer, to get more accurate readings, the meters are to be connected in the following sequence of the supply: voltmeter, ammeter, wattmeter, ammeter, wattmeter and voltmeter, wattmeter, voltmeter and ammeter, voltmeter, ammeter, wattmeter and ammeter. Suppose in this one is the supply voltage, V here, and this is the auto transformer or the variac. After the variac, so we need to connect the voltmeter, so this which measure the voltage, and after that the wattmeter reading. So this wattmeter, so it is a wattmeters, W, naught, and it is a V naught, and then after ammeter, so which measure the I naught. So now this one is the primary winding of the transformer and this is the secondary winding of transformer. So it is a open. So now this LV is winding and this one is the HV winding of the transformer. So in case of open circuit test, this is the sequence from the supply side: voltmeter, wattmeter and ammeter. So option the 4 is the correct for this question. Exactly to get the accurate readings, what we have to connect: voltmeter connect across the supply, then after wattmeter and the ammeters. Clear? And next one, let us solve the question number 132. The maximum efficiency of a single phase transformer is 97%, the which occurs at 90% of the full load kVA at 0.8 power factor. So if the power factor is 0.9, so maximum efficiency at the same load is, so more than the 97%, between the 91% to the 96%, equal to the 97% and less than the 97%. So variation of the percentage efficiency, so with respect to the power factor curve. So from this case, so let us take this percentage efficiency of the transformer, and this one is a current, this power factor here. So now this is the 0 power factor, 0.2 power factor, 0.4, the 0.6, 0.8, and this one is the 0.1 power unity power factors. So maximum efficiency occurs at unity power factor in general. So this is the variation of the efficiency with respect to the power factor angle. So maximum efficiency of single phase transformer at 90% of the full load current. So full load and the at 0.8. So now the power factor is 0.9. Then what will happen? So initially at 0.8 power factor, so this under this condition, so this efficiency is equal to 97%. Now at 0.9 definitely it is a more than, so this one is a here. So now it is a greater than the 97%. So like this also we can answer, other way also we can find out. So first one we know the formula to find out maximum efficiency. So now this is a percentage maximum efficiency is equal to S into X, the S okay cos theta, S is a VA rating, cos theta 2, X into S cos theta 2 plus 2 times of the iron losses multiplied by 100. So from this equation find out the 2 times of iron losses. So we will get this point, and here X cos theta is equal, suppose for 0.97 the multiplied by full load condition, the S into cos theta 0.8, so divided by 1 into S into 0.8 plus 2 times of the iron losses. So by using this you can get the 2 times of iron losses. So now this one is a 0.8 times by 0.97 minus 0.8 into S. So 0.8. We got the iron losses. Now just substitute this iron losses in the another efficiency formula. So now this one is X into S, the cos theta 2 divided by, so X into S, the X value is equal to again 1, the S, but this value cos theta is of 0.9. The 1 into S into 0.9, the plus okay this value, so this one is a 0.8 S divided by 0.97 minus 0.8 S. So now by solving this, so we will get, so 97.67 something nearly equal to this part. So now which is greater than the 97%? Like this also we can answer, but it needs the calculation part. So that's why better to use this method to answer this question. Just use the curve, so we can answer the question. So that answer for this question is option 1 is the correct. Okay, we can get the answer by using formula or by using the curves, both ways also, but it takes time, it needs calculation. This is one of the best analysis method to answer this question. And next let us solve the question number 133. All day efficiency of the distribution transformer is equal to the commercial efficiency at a load less than the full load kVA at particular power factor less than UPF. When it is operated the dash for the 24 hours of the day, same kVA load and unity power factor, and full load kVA and same power factor, same kVA load and same power factor, full load kVA and the unity power factors. All day efficiency means the efficiency of the distribution transformer is calculated based on the energy. So this efficiency is known as all day efficiency. The efficiency of the power transformer which is used in the transmission system is calculated based on the power. So in order to get these two are equal, these two transformers must have the same kVA load and the same power factors. So that option, the 2 is the correct for this question. And next let us solve the question number 134. Delta 3 phase 50 Hz 200 kVA transformer is connected as open delta. So then the rating will be reduced by approximately 133.3 kVA, 1.5 kVA, 84.5 kVA, the 66.6 kVA. So this is the rating of the 3 phase transformer closed delta connection. So we know that capacity of, okay, this capacity of the open delta connection, open delta 3 phase transformer divided by the capacity of the closed delta 3 phase transformer, the open delta 3 phase transformer divided by the closed delta 3 phase transformer connection. So now this is equal to the root 3 times of the V pace multiplied by I pace. Now this one is the root 3, this is the 3 times of the V pace and the I pace values. So Vp and this is the V is a cancelled, I is a cancelled out. So this is equal to 1 by the root 3 times. Now capacity of, okay, this one capacity of the open delta connection, open delta 3 phase transformer, the is equal to 1 by root 3 times, 1 by the root 3 times of 1 by root 3 means 0.57 the 7, okay, 0.57 times, okay, this one is 0.57 the 70 times of the capacity of the closed delta 3 phase transformer connection. So this 3 phase transformer. Now how much reduction here? The reduction in the per unit value, okay, this one is reduction in per unit value 1 minus 0.5732, or this one is equal to 0.4 the 2, okay, 427. So now this is the reduction in the per unit value. The reduction in the per unit value per 100 kVA, reduction in the percentage. So reduction the in percentage is equal to 42.7%. Per 100 kVA it is a 42.7%. So reduction, total reduction is equal to total, the reduction in the total reduction or total reduction in the kVA, the kVA is equal to 42.7 divided by 100 multiplied by 200 kVA. So this value is equal to 84.5 the kVA. So answer for this question, and reduction reduced by the approximately 84.5 kVA. So answer the 3 is the correct for this question. Got it? And next one, let us solve the question number 135. In a 3 phase alternator, the magnetic poles are located in the stator and excited by AC source, the stator and excited by DC source, the rotor and excited by AC source, and rotor excited by the DC source. Magnetic poles are placed in the rotor which are excited by the DC source to produce the steady nature of the magnetic field. So option the 4 is the correct for this question.